we continue on the integer programming problem. We look at a group assignment problem. So we will consider the problem of forming 10 committees of each of which have 10 persons, and the total number is 100 people. So the goal is that each person is on one committee only, and no committee has two people who hate each other. And we ask everyone for their first five choices of committees, and we assign everyone to one of their first five choices and try to give as many people their first choice as possible. And so we define the set of A to be a couple, a pair of I and J. So persons I and J hate each other. So these are the set of people who hate each other. And we also define the set of B index K. So the set of B index K is a person I who can serve on committee K. Okay, so there's an index K here and K here. And this occurs if person I has chosen K as one of their top five choices. And we define this is just the parameters. So dik equal to 1 if committee K is persons I first choice and 0 otherwise. And so now we define decision variables. So decision variables are xik. So sometimes we call these assignment variables. So xik is 1 if person I is assigned to committee K and 0 otherwise. So the objective is to maximize people first choice. So we maximize the xik, and I is from person 1 to person 100, and K is committee 1 to committee 10, and each person is on one committee. So we sum over all committee for xik, and then actually I made a mistake. So this should be 10 only. So this is 10. So for everyone, for person 1 to 100, so we have this constraint, and each committee consists of 10 people. So we sum over all. So for each committee K, so um, there are only 10 people. So K can go from 1 to 10. And then the interesting constraint is that no committee has two persons who hate each other. So notice that we fix the K. We fix the K. So given the same K, xik plus xjk is less than or equal to 1. And for I and J in set A up here, so A is a set of people who hate each other. So if I and J is in this set, this condition has to be true. So I and J are not going to be on the same committee K. And then also everyone is assigned to one of their first five choices. So for people I, in the set BK, then XIK is either 0 or 1. But if the person I is not in the set BK, then XIK is 0. Okay, so this is an assignment problems. And then the next problem that we look at is set covering and packing problem. So in some selection problems, each item is associated with a subset of a larger set. The larger set is usually referred to as the ground set. For example, suppose there's a collection of n set S1 to Sn, where for I from 1 to n, Si is the subset of the ground set. So maybe it's easier to look at the problem instead. So we have parameters Aij. So Aij is 1 if I is in the set Sj and 0 otherwise. So we have the decision variable Xj is 1 if Sj set J is selected and 0 otherwise. Okay, so we can have a problem of set packing problems. These points are in more than one set. Okay, so you can see that this one is in set this one and also the green one. And okay, so we want to have as few set as possible in such a way that it still covers all these dots. Okay, so we can see that the minimum number of set is 1, 2, 3, and 4. We can see the application of the set packing problem. So scheduling airline flight crews to airplanes is another application of the set packing. So each airplane in the fleet need to have a crew assigned to it. A crew consists of pilot, co-pilot, and navigators, and also flight attendants. There are constraints on the composition of possible crews based on their training to fly different types of airplanes, as well as any personality conflicts, like some pilots might not like each other. So, given all possible crew and plane combinations, each represented by a subset of items, we need an assignment such that each plane and each person is in exactly one chosen combination. After all, the same person cannot be on two different airplanes, and every airplane needs a crew. So we need a perfect packing given the subset constraints. Okay, so this is so another application of set packing problem is the graph coloring problem. So this is a map of counties in Colorado, and we the problem is we want to find the fewest number of colors needed to color all of the counties, so that no counties with a common border have the same color. Okay, so we want to find. So this is the goal: fewest number of colors needed. Yeah, so this is Colorado counties without color, and this is Colorado counties with four colors. Okay, so this is actually a hard problem to solve, and lately it has just been solved optimally. So we can form this problem as an integer program. So the graph consists of the node and the arcs, okay? And the node are like 1, 2, 3 until n set of counties. And so um, the pair ij is in the set A if counties I and j are adjacent, they're next to each other. So we define decision variables. Yk is 1 if color k is used, and yk is 0 if color k is not used. So this has to do with color. Okay, and xik has to do with region I is given color k. Okay, xik. So so now we have four colors k from 1 to 4. So we want to find an assignment to see which counties should be painted in what color. So the objective is to minimize the number of colors. So we want to minimize yk, the sum of yk. And then we have to say that each county is given one color. So x for every county I, the sum is give fixing the I, the sum over k is 1. Okay, so if counties I and j share a common boundary, they are not both assigned the same color. So we can say that if I and j is in set A, so if I and j are adjacent, then it should not be given the same color k. So we can say that xik plus xjk less than or equal to 1 for ij in the adjacent set. And then we also need a relationship between x and the y. So if county I is assigned color k, then color k needs to be used. So if xik is 1, then it automatically forces yk to be 1. Okay, so if xik is 0, then yik can be either 0 or 1. Okay, and then the last constraint says about the yk and xik being a decision variables like this. Okay, and then next we you might wonder about the application of the graph coloring problems, and one application that I can find is exam scheduling. So suppose a university has 500 exams in 28 time periods. And we want to schedule so that there's no time conflict for students. So the county can be exams and the color are exam period. Okay. So so for each, so okay, we have xik to be 1 if exam I is in period k and 0 otherwise. And so then we have to have a constraint that exam I and j cannot be in the same period. For okay, I forgot to say something about the set A. So our set A is that um, um, s- so so a person I needs to take exam I and J, so they cannot be in the same time period. All right, so exam I and exam J cannot be in the same time period if there's a student who needs to take it. So once we form a set A of the exams that cannot be in the same time, we can have this constraint that xik plus xjk cannot be in the same time period k. Okay, so we look at the set packing problem, and now we are going to look at set covering problem. Okay, so the idea, again, we look at like a map, and then here we have a bank operation, and so we have the banks wants to cover 20 counties. Okay, and so currently the bank does not have a principal place of business in any of the 20 countries. So according to the banking laws in Ohio, if a bank establishes a principal place of business in any county, branch banks can be established in that county and in any adjacent county. However, to establish a new PPB, Ohio Trust must either obtain approval for a new bank or purchase an existing bank. So the table above lists the 20 counties in the region and the adjacent counties. For example, here, number one, Ashtabula is next to, let me see, number one, Ashtabula is next to number two, number 12, and number 16. Okay. So so the idea is that they want to find a minimum number of bank branch so that it can cover the 20 counties. So for example, if I set it up in number 12, so customers can county 1, 2, 3, 13, and 16 can come to this. So it's like so yeah, the branch in county 12 can take care of itself, and county number 1, 2, 3, 13, and 16. Okay, so the so the goal is to find the minimum number of branch necessary to do business throughout the 20 county region. So we define aij, so these are parameters. Aij is 1 if location I is adjacent to like location j and 0 otherwise. And so we can get aij from the map. And then we define the decision variables. So for example, just to make sure you understand aij, for example, if we look here, so A112 is 1, and A12 is 1, A116 is also 1, and so on. And then A115 is 0, and A114 is also 0. So aij is just tell us about if county I is next to county j, and we can get the aij from the map. So, and then we can also have the decision variables yj equal to 1 if county J is chosen to set up a bank branch, and 0 if it's not chosen for a bank branch. And so we want to minimize the total number of branch that we need. So we minimize the y1, the sum of y1 to y20. And then we also need a constraint that every county is covered by some PPB. Yeah. So we fix the county I. So A1JYJ, and we sum over from J from 120 has to be at least 1. And in general form, in any I, so we have summation of AIJYJ greater than or equal to 1. Okay, so we going to look at these problems on Excel. So here's the data from the problem. So we have to first create a covering matrix. So here um, we need to create the adjacent matrix Aij. So this is our I, and up here is our J. So remember that Aij is 1 if county I is next to county J. So we can create the adjacent matrix with using Excel formula here. So we just want to check if we go row by row. So we have to check if county I is in this set. So we check. So I'm going to remove this one. So um, we check if county in cell L3 is in this list. If it is in, so if this one is in this list, so you can see that I fix column A to column I, and then if L4 is in this list, then it's greater than or equal greater than 0, then the value is 1 else 0. Okay, so you can copy this formula out. So you can see that this formula actually works because we want this one, we want A11 to be 1, A11 to be 1, A12 to be 1, and also A112 to be 1, and A116 to be 1. Okay, so it works for the first row, and then let's check the second row. So, and here, so instead of fixing on row 5, now we move to row 6, and we can copy them. Okay, so so A21, A22, A23, and A212 is 1. Okay, so I'm going to remove the, and then I can just copy them down. So here, just to check with the last row, so A20 11 is 1, A2014 is 1, and A2019 and 20 is 1. Okay, so we have to check if, so this is our decision variables. So these are binary, either 0 or 1. So the objective is to find how many branch bank branches do we need. So we sum this. Okay, this is the objective, and we want to check if every county is covered. So we can just do essentially A11 Y1, A12 Y2, and so on. So we can just do some product of this and this. We just want to check if county I is covered. And then I need to freeze row 14 or row 4, I'm sorry, using function F4. I freeze this, okay, and then I can just copy them down. So just check, so as some product this and that. Remember that our constraint is this one. So what Aij, Yj is at least one for every county I. So this is essentially the sum product of row vector y and row vector of a ij, fixing the row I. Okay, so here I have this. So now I call up the solver, data solver, and then here I want to select the objective to be aj2, and I want to minimize. Changing variable cells are decision variables are these ones. And I add a constraint that every county is covered. So greater than or equal to 1. And I add the constraint that the decision variables are binary. And and then so here again, the objective is to minimize the number of bank branches that we need to set up, and we want every county to be covered. I mean, at least there's a bank branch in itself in that county, or some or any county next to it. Okay, so I'm going to click solve, and then so the decision variable is found. So you can see that every county is covered, and there's some county like county 8 or county 10, 13, 18 is covered by more than one bank branch, and the number of bank branches that we need is some 3. The objective is 3, so we set it up at county 7, 11, and 12. So if you go back to see this, so you can see that just having the bank branches at these 3 counties is enough to cover the entire state, meaning that there's enough to take care of itself and also counties next to it.